Welcome to this last lecture for chapter 22. Today I'm going to continue talking about amines, and I will explain two types of reactions. There's two big topics. One is some special considerations for electrophilic aromatic substitution, and the second new topic is this concept of nitrosation, which introduces a whole bunch of new chemical reactions that you can do using a benzene ring. But first, let's start with a review quiz. Now, here's the first review quiz. As always, pause the video for a second and give yourself a chance to come up with your own answer. Okay, let's see how you did. This question requires you first to come up with the correct structure, and then we're going to heat this in the presence of hydroxide. The hydroxide should pull the hydrogen from the Hofmann position. So here is the leaving group. There's the alpha carbon. This is a beta carbon with 3 hydrogens. This is the the equivalent beta carbon with 3 hydrogens, and then this beta carbon down here only has 1 hydrogen. So Zaitsev would tell us to take the hydrogen from here, but Hofmann tells us with a sterically bulky leaving group you want to pull the hydrogen off of one of these two positions, and then it will give you this product right here. The name for this, you just have to draw it. So this is, if you drew this correctly, then you got it. If you want to name it, there's a little bit of review of alkene nomenclature. One of the key problems with thinking about Hofmann elimination is remembering to show the Newman projections. This question didn't ask you to show them, but let's take a look at what the two different Newman projections would look like. This again is your alpha carbon. These two beta carbons are equivalent, so one of my Newman projections should look at elimination along this bond right here. This is the non-equivalent beta carbon, so my other Newman projection should look at elimination along this bond right here. This Newman projection, let's see which one this is. Yeah, this Newman projection is looking at this carbon in front. That is the carbon that is directly connected to the nitrogen, so that's the carbon that's in front. And the carbon in back is a methyl group, so it would be this carbon right here. In order for elimination to occur, the leaving group must be anti relative to the hydrogen. And since this back carbon, no matter how it turns, you have 3 hydrogens, every time you would expect one of those hydrogens to be in the correct orientation for an elimination to occur. So this is an easy elimination to occur because the hydrogens are always going to be lined up anti relative to your leaving group. If instead we look at this Newman projection, which still puts the carbon connected to the nitrogen in front, so that's this carbon right here, and the carbon in the back is the one with 2 ethyl groups coming off of it, so it's this carbon in back. In order for the hydrogen on the back carbon to line up anti relative to the leaving group, which must occur in order for elimination to happen, those 2 ethyl groups are forced into a sterically, this is pretty extreme position right here. It's gauche on both sides. Ethyl groups are larger. It just is such a low probability that this hydrogen would be found in this particular staggered conformation. Much more probable for the hydrogen to roll over to one of these positions to reduce some of the steric strain across the molecule. Since this leaving group here is so sterically bulky, it pushes the ethyl groups over to the anti position, puts the hydrogen in a position where elimination can occur, so we don't expect for the molecule to line up in a way that's favorable for elimination to produce the double bond at this position. If you're struggling with these Hofmann elimination and thinking about the Newman projections, it would be helpful to break out your model kit if you have one. One more, name the major Hofmann product formed when 2-ethyl-NNN1 tetramethyl cyclopentaminium hydroxide is heated. That's a mouthful. I'll pause the video and give you a chance to answer this question. Here we go. This is the starting material, and this is more of a nomenclature question at this point. I've given you the starting material via name, and your job is to come up with the product. You were supposed to name this product. The hydroxide is going to pull the hydrogen from the Hofmann position. So this is my leaving group. That's the alpha carbon, beta, beta, beta. These 3 beta positions are all non-equivalent, which means I need to think about them separately. This beta carbon has the most hydrogens, this one has 2 hydrogens, and this one right here has 1 hydrogen. Zaitsev would tell you to take it from this hydrogen. Hoffman tells you to take, Zaitsev would tell you to take this hydrogen. Hoffman would tell you to take it from this carbon, and nobody wants you to pull from this carbon over here. This ends up being the final product. The nomenclature on this is interesting because it has a methylene group. Methylene is a unique common name for a substituent. It's when a carbon is doubly bound into the parent chain. It's one of the few times that a substituent doesn't end in a YL ending. Okay, topic number 1, electrophilic aromatic substitution. This is a review of one of the first mechanisms that you saw this semester. In the presence of iron tribromide as a catalyst or iron 3 bromide as a catalyst, depending on if you are considering it to be ionic or covalent, that's how you would change the name. Anyway, bromine, molecular bromine, plugs into the iron center and activates this external bromine here as a strong electrophile. That causes the ring system to reach out, breaking the aromaticity, and then in the second step we restore the aromaticity. Breaking the aromaticity is the rate determining step. Restoring the aromaticity gets you back to your final product. This is referred to as electrophilic aromatic substitution. This is a review. This chapter talks about amines, and aniline is the aromatic version of an amine. Aniline is kind of OP. The nitrogen's lone pair gets sucked down into the ring system, and this thing reaches out to gobble up bromine electrophiles without even needing an iron catalyst. And so we break the aromaticity in the first step, and then we restore the aromaticity in the second step. This is an ortho-para directing substituent, so you can put it at either the ortho or the para position. I chose the ortho position partly because it fit on the slide a little bit better when I did that, but also because you have 2 separate ortho positions and only 1 para position. So even though the para position is more probable than a single ortho position, having 2 ortho positions makes it more likely for a monobromination to end up at the ortho position with this sterically unencumbered or a very small directing substituent. But all of that really doesn't matter because this is such a powerful directing substituent that it's difficult to control it, and it will continue to brominate until at least all of the ortho and para positions are filled. If you remember this table from previous lectures, activating substituents, this is for electrophilic aromatic substitution. The most activating substituent is that amino group, meaning aniline is the most activated compound that we typically encounter. It's even more activated to have an NH2 group than to have an OH group because the nitrogen is less electronegative and is better able to push its electrons down into the ring system and facilitate the pi bond reaching out to pick up an electrophile. So this means that the system's kind of broken. You can't just put a bromine on aniline and expect one bromine to end up there. So there is a laboratory-based solution. One of the common undergraduate laboratories that I've run with students in the past is the electrophilic aromatic substitution of acetanilide to yield 4-bromoacetanilide. Acetanilide does not have the same problems that aniline has. Aniline is too reactive. When you acetylate aniline to generate acetanilide, this carbonyl group right here has causes resonance delocalization of this lone pair, and it pushes over here into the oxygen. That makes acetanilide less reactive for electrophilic aromatic substitution because instead of the lone pair dropping down into the ring system and facilitating the electrophilic aromatic substitution, the lone pair kind of cheats out towards this oxygen. So it dampens the reactivity of this nitrogen as an activating substituent. Mechanistically, we're going to look at that now, but let's first look at the reaction. Aniline, when you try to react it with bromine, even if you take away the catalyst, this is just a solvent right here, it will end up not producing the mono-bromo product. You'll end up with a tri-bromo product. So if we want the mono-bromo product, if this is the chemistry that we want, we have a bit of a long pathway to do. And that pathway first involves the addition of an acetyl group to your nitrogen, and then you carry out the bromination. Notice how still I don't use the iron catalyst. And again, I've run this in the laboratory. Well, I've watched undergraduates run it in the laboratory, and even they are able to accomplish this reaction in high yield. So this works really well. And it generally produces exclusively the para-bromo product. This is a large, sterically bulky substituent and tends to prevent the bromination at the ortho positions. Plus, this bromine is deactivating a little bit. It's not very strongly deactivating, but that means that once you put the bromine on there, then the product is less reactive. And that enables the reactant to react with all of the bromine before the product does. So, easy to do. Then this is now an amide, and in the previous chapter we looked at hydrolysis of an amide. This is a base catalyzed hydrolysis of an amide to get back to just the aniline right there. And so these 1, 2, 3 steps are how you accomplish a monobromination of aniline. The mechanism for that reaction. Here is the acylation mechanism. So here I have acetic anhydride, and I've drawn the structure of acetic anhydride to be as simple as possible to illustrate the point that acetic anhydride is mechanistically identical to acetyl chloride. So this is the anhydride portion. If you want, you can just pretend that that's a chlorine atom there, and the mechanism is identical. The nucleophile, under typically basic conditions, because aniline is a weak base, will push into the carbonyl carbon. We generate an oxide ion, which is allowed under basic conditions. We deprotonate the nitrogen nucleophile, and then the tetrahedral intermediate collapses and bumps off an acetate. That acetate would eventually cycle over and deprotonate the aniline so that we don't end up using 2 equivalents of aniline. But that's not involved with the organic chemistry that I care about, so I left that step out. So these 3 steps right here are the acylation. It's how you add an acetyl group to your aniline to get the acetanilide. The next step is the electrophilic aromatic substitution step, and I skipped the mechanism for that one because I just showed it on the previous slide, and this slide is running out of room quickly. And then the last step is the hydrolysis step, the base catalyzed hydrolysis. Potassium hydroxide is added, ethanol is the solvent, hydroxide plugs into the carbonyl group. Again, under basic conditions, it's not a problem to have a negatively charged oxygen. That slides down and bumps off this ion. Normally, we don't like to see negatively charged nitrogens, even in a basic solution, but the unique resonance delocalization of the lone pair into the ring system makes it reasonable for us to bump off the nitrogen without pre-protonating it. So we post-protonate it to get the hydroxide back. It's catalytic, and we end up with our final product. So from start to finish, we took aniline and we put a bromine on there. And it's just one molecule. It's not like a big deal that you know how to put a bromine directly on aniline, but it's the overall principle. Acylation is a way of tempering the reactivity for electrophilic aromatic substitution of aniline, and then you can carry out the chemistry, and then you clip the acetyl group off using a base, or you could do it with an acid as well. Topic number 2, nitrosation. Nitrosation is the addition of the nitrosyl cation to an amine. Aqueous nitrous acid, so nitric acid is HNO3, nitrous acid is HNO2. Under aqueous conditions, this decomposes readily to things that act like the nitrosyl cation. So for the sake of simplicity, we just show the nitrosyl cation. This is a very reactive electrophile. Secondary amines can plug directly into the nitrosyl cation, and it gets turned into a nitroso group. Okay, this is nitrosoamine right here. Notice that in order for the chemistry to finish, you do have to remove a hydrogen. That means that if this is a tertiary amine and does not have a hydrogen that's present, when the nitrogen plugs into the nitrosyl cation and you can't lock it on there by pulling the hydrogen off, the nitrosyl cation comes off. So we don't look at this reaction with tertiary amines. Secondary amines end up producing this nitrosoamine. And synthetically, that's not something we're interested in. biologically it's pretty interesting. There's a variety of different nitroso compounds that show up in some of the foods that we eat that are not necessarily good health choice foods. Beer and other compounds, and other substances will produce this nitrosoamine. This one tends to show up in cigarette smoke residue, and bacon tends to produce this particular nitrosoamine, all three of which are carcinogenic. And so this right here seems like a barbecue going on. You end up with a lot of carcinogenic compounds, and so this is one of the reasons why nitrites, which are the conjugate base of nitrous acid, so nitrite is NO2 minus, is a known carcinogen. When it gets protonated to produce nitrous acid and heated up, it generates the nitrosyl cation, which can then nitrosate compounds in your food. And this is why some people look very carefully for packaging to avoid nitrites. Primary amine nitrosation is what's really interesting to us. And this is just a simple primary amine, and we're going to think about R here as an alkyl group. This can plug into the nitrosyl cation. We remove the first hydrogen to get the nitrosoamine, and then the lone pair slides down as that protonates under acidic conditions, and we remove the second hydrogen. Mechanistically, we're going to look at this in another slide, and I'll slow down and walk through it a little more slowly. But notice that there's the second deprotonation step that has to occur, and this ultimately ends up producing an alkyl diazonium ion that decomposes to generate a carbocation. This was a primary amine that can easily generate a carbocation, which ends up being a primary carbocation. So this is one of the few mechanisms whereby, with a little heat, we actually get primary carbocation formation. Primary amines will form this carbocation, and then typically they run this in the presence of water. Water rapidly jumps on the carbocation, and you end up making an alcohol directly from an amine. So that's kind of useful. If you think about there, we have three different flavors of amines: primary and secondary and tertiary amines. The secondary amines were the ones that I showed you first. They produce the nitrosoamines, which are really not very useful unless you're interested in generating cancer. The primary amines can form a carbocation that gets quenched by water to make alcohols. And the tertiary amines don't do a lot at all when they're an alkyl amine. So moving from alkyl amines to aryl amines, that's where we start to see something much more interesting. And it's really only the primary aryl amines. So here's kind of the slide of reactions that nobody cares about. Tertiary aliphatic amines don't react. Tertiary aryl amines will undergo electrophilic aromatic substitution to produce a nitrosoaniline compound. Secondary aryl amines form these carcinogenic nitrosoamines that people really try to avoid. There are some mechanistic endpoints where these are a useful intermediate. We won't look at any. Which finally gets us to the thing we actually care about, and these are primary aryl amines. And there's really only one primary aryl amine that we're interested in, and that's aniline. So all of that to say that aniline is the compound we care about. So now we're finally talking about the thing that matters the most when it comes to the nitrosyl cation, and that's aniline. And we can look at other aniline derivatives, but really only things that have stuff hanging off the benzene ring. We need the NH2 group to kind of be left alone for this to work the way we want it to work. And what we're trying to do is convert an aniline into an aryl diazonium ion. And the mechanism for this is identical to the primary alkyl amine. The electrons from the aniline plug into the nitrosyl cation as an electrophile. There's a deprotonation, internal nucleophilic shuffling, a second deprotonation event. We protonate the leaving group. The electrons slide down to make the triple bond, and we bounce off water. And we have this aryl diazonium ion right here. This can decompose if you add heat to the system, or we can prevent it from decomposing by keeping the system cold. So we control it, whether we keep it as the aryl diazonium ion or we go ahead and cook it off to generate a phenyl cation. So here's that step. Here's the aryl diazonium ion. Here's the addition of heat. Mechanistically, it's just one little curved arrow. These electrons leave on the N2, and it comes off as molecular nitrogen. This is an incredibly unstable cation, but this is an incredibly good leaving group. And we already saw this previously with alkylamines when they form the alkyl diazonium ion. That thing cooks off to form a primary carbocation, which has never happened in a useful synthesis up to this point in the course. So the question now is, what can we do with this thing? And the answer is a lot, because this is a reactive electrophile, and we can plug all different kinds of nucleophiles on there. And basically we now have a way of adding essentially any compound we want directly to a benzene ring. The easiest thing we can do is put water inside the system. So here we have aniline. We add in our nitrite. We acidify the solution. This, in an inorganic reaction, the nitrite will react with one of the hydrogens on sulfuric acid to produce nitrous acid. That decomposes to produce the nitrosyl cation, and then this aniline reacts with the nitrosyl cation via the mechanism that I showed on this slide right here, ultimately to produce that aryl diazonium ion. Check to see what the temperature conditions are that are specified. Here heat is specified, meaning that once you get the aryl diazonium ion, that N2 will fall off to produce a phenylcation, and now the phenylcation will react with whatever nucleophile it can find in solution. And when water is present, you typically expect water to do as much chemistry as possible. So under these conditions, water will jump on to that cation, and we end up making phenol. So this is a one-pot synthesis going from aniline to phenol, which some of you might find useful if you're writing a report for the chemical company activity. What else can we do? This table right here gives us a bunch of different things or options that are available for the aryl diazonium ion. And synthetically, this is really cool. This is another one of those wheels where, starting from a central compound, we can branch off in a variety of different directions. So I'm not going to worry about the mechanisms for these reactions aside from the first one, just water. So once you get to the aryl diazonium ion, you should be able to show a mechanism going from benzene all the way to the aryl diazonium ion. From that point, the only mechanism that you need to be able to show is the aryl diazonium ion falling off and water replacing it, and then deprotonating the water to end up with a phenol. For the rest of these, it's just a list of reagents that you kind of have to memorize. Let's apply this to a specific question. Show a synthetic scheme for the production of 1,3,5-tribromobenzene from benzene. And if you didn't understand anything we're talking about today, you might try this mechanism, this reaction, where, well, I need to put a bromo group on a benzene. So I'm going to use electrophilic aromatic substitution and catalytic bromination of my benzene. You run it once, and a bromine adds. And then you try it again, but this bromine right here is ortho-para-directing. So the second round would put a bromine here at this ortho position, and we now have 1,2-dibromobenzene, and we're nowhere close to the compound that we want, 1,3,5-tribromobenzene. So this is where we need to go back and use this synthetic route that I just showed on the previous slide. We're going to make an aryl diazonium ion, and then we're going to cook that thing off and replace it with a hydrogen. So synthetically, we put a nitro group on, and then we reduce the nitro group to end up with an aniline. This is a mechanism that you're responsible for. This is not a mechanism that you need to know. Then, once the NH2 group is on here, we can use electrophilic aromatic substitution with molecular bromine. No catalyst is necessary, and let this thing go crazy. And it will put bromines at all three positions. Once the bromines are on, we now have the 1,3,5-tribromobenzene with this NH2 group that we need to get rid of. So in the presence of acidic conditions and nitrite, under cold conditions, we turn the NH2 amino group into the diazonium ion. And we want to keep that thing from falling off, because if you leave it, if you try to cook this thing off, there's plenty of water present whenever you have sulfuric acid, and you'd end up putting an alcohol on, and that would be really difficult to get off. So you leave it cold, and then you isolate this as an ion all by itself, and then you put it under either ethanol, or this is hypophosphorous acid, I believe is the name of that compound. And if we go back to the table on this previous one, when you have the aryl diazonium ion, you can add either of these two reagents, and that removes the diazonium ion and replaces it with a hydrogen. So that's how we would finally get this nitrogen off. The nitrogen needed to be there to direct the orientation of the bromines to the correct position, and then we get rid of it. So we added the nitrogen, we used it, and then we took it off, and we got the bromines on where they're supposed to be. Something else that we can do with the aryl diazonium ion that does not show up on that previous table is something called azo coupling. This is actually really useful if you're trying to make large conjugated systems, and I'll explain why we'd want those in a second. But in the presence of some type of electron donating group, such as an NH2 or an OH or something that can push electrons directly into the benzene ring system, a benzene ring will actually attack the aryl diazonium ion. This is a good electrophile, and we break the aromaticity. Then a base is going to come along and restore the aromaticity, and we have what's called a diazo coupled compound, where we have a benzene ring over here that's bridged through two nitrogens to another benzene ring. This is useful if you look at these two food dyes, yellow dye number 5 and red dye number 40. They were synthesized via a diazo coupling reaction, where, and I'm not sure which one, you could do it either way. You put the diazonium ion on this ring system, and electrophilic aromatic substitution will push into that through this ring. And this one right here, there's your diazo coupling. So the aryl diazonium ion would probably be this compound, and this reactive nucleophilic pi system would push into that nitrogen. So this is how they synthesize these food dyes, and this type of diazo coupling reaction is one that we used to run in the laboratory years ago with students. It's pretty effective, it's easy to run. It's just a good example of another example of electrophilic aromatic substitution.